Professor?
Yep, what's up?
Just a quick comment on my feedback for the project proposal in 410.
Yep.
I was doing a building with an earthquake simulation.
Yep.
And in the feedback, you said, I wonder if there's a way to use a dynamic analysis of some sort to apply sinusoidal shaking.
Yep. Mm-hmm.
Yeah, I looked into that, and it turns out, well, I feel harmonic response analysis would be exactly that.
Okay. Okay.
Yeah, and you said you do that to make it like graduate level.
Yes.
Yeah,
Yeah.
so I'll definitely be doing that.
Okay. Okay. Yeah, that sounds good. Yeah, I wasn't aware. I've heard of harmonic analysis before, but I've never seen it or really tried it. And so, yeah, if you could explore that for your final project, that'd be good.
Okay, definitely. Thanks.
All right, it's 5:30, so let's go ahead and get started today. All right, good evening, everyone. How's everyone doing today? How was your weekend? Everyone's tired, I bet. I've heard it's another midterms week, and so yeah, it's time for that second wave of midterms. Yeah, very tired. Yes, it's yeah, I can't imagine what you guys are going through with, especially a lot of you seniors too. So I know like this is the time when senior design like really starts to ramp up and get really stressful. I can't even more so with the with the pandemic and everything. Yes. Yes. So yes, our midterm is next week, and so I do want to spend today talking about that. And so yeah, speaking of midterm, so ours is next week, right? And so let's talk about that first, right? And so our next midterm will be next Wednesday. (4/21), okay, right? And it's going to be in class, just like the first one, right? How many homeworks are left? There's only one homework left, and so I only have 6 homeworks for this class, and so the next homework will be after the midterm. Yeah, so I just realized today that it's right after 420, so I apologize. So if you're looking forward to enjoying 420, maybe you enjoy it a little bit less because there's a midterm the next days. But if you have stuff, hopefully you can enjoy it after the midterm. Yeah. Okay. And so the format for the midterm is going to be exactly the same as the first one, and so it's going to be in class, 90 minutes. Okay. Right. So you're just going to sign in here. And you're going to take the exam on Canvas, right? So you can come to the Canvas, you can come to the Zoom lecture, or you cannot, right? Okay. There's going to be 3 conceptual questions, and those are going to be short answer. And 2, I call them problem solving, but you're not really problem solving in this case because you're kind of writing the pseudocode, but it's kind of in exactly in the same style as the first midterm, where I want you guys to take the methodology and apply it to a certain equation. Okay. All right. So there's going to be no MATLAB. It's all just going to be pencil and paper type of calculations. Right, and so in terms of the content that I expect you guys to know for the exam, it's basically going to be homeworks 4 and 5. right? So homework 4 is the one you turned in right before spring break. Homework 5 is the one that's due this Wednesday. Okay. Right. And so if you look at the styles of those problems, for the conceptual problems and for the problem-solving ones, you're going to be in good shape. Right? Just like last time, I posted a study guide on Canvas, and so you can go ahead and check that out as well. And so you can find the study guide for on the page for week 12. Okay. And just like last time, I'll post a poll probably sometime on Wednesday, so you can vote on your most uncomfortable topics. And then Friday, I'll record a review video to help you study as well. Problem solving like the last exam. Yeah. And so it's going to be basically, here's an equation. I want you to apply, either finite difference, finite volume, and then write out the algebraic equations for this problem. Yeah. And so since, the topic for this exam is going to be time marching schemes and basically diffusion with finite volumes. And so you can generally expect, one problem, time marching problem, explicit Euler, implicit Euler, and then the other problem will be, apply finite volumes for diffusion. Yeah. Yes. So I'm going to record a review video probably sometime on Friday afternoon, so that you can have that for the exam as well. So I'll put a poll up probably on Wednesday, and then I'll close the poll probably sometime Friday morning, and then I'll record the video and I'll send it to everyone as well. Yeah. Okay. And so in terms of same rules apply as the first midterm, and so it's an individual exam, so please don't talk to anyone. But besides that, and besides using an outside source, you can use any of your notes, any of the homework solutions, any of the lecture notes, lecture videos, whatever you want for the exam. Yeah. So just no communicating with other students, and no posting the exam questions on other websites. Okay. So any questions on the exam or anything before we get started today? All right. So let's go ahead and get rolling. And we're moving on to the next topic in finite volumes, which is convection. Okay. Right. Since it's this is coming up right before the midterm, and it's the homework 5 doesn't cover this, convection with finite volumes, this is not going to be on the exam. Okay.
So all the way to notes 10, that's going to be on the midterm, right?
Correct. Yes. Okay. Yeah. Mm-hmm. All right. So it's not going to be on the midterm exam, but if you we are going to have a homework for this after the midterm, and if you're going to do the final project with finite volumes, either you choose to do so, or you're a graduate student, then you're going to need this information. Okay. All right. And so we all know what convection is at this point. So convection, we know is just the active transport of a material through a moving fluid. Okay. Okay. And so that's still the same. So the only thing that's going to be different now is how we discretize the equations. Okay. All right. And so let's go ahead and write out the our differential equation. I'm going to put it in vector form just so that we can kind of work with it from there. Okay. And so the vector form of the equation with convection looks like the following. Okay. And so first we have the divergence of the velocity vector times phi minus k, divergence of the gradient of phi, okay, and this is equal to q. And so this looks like exactly the same equation that we were working with last week. The only difference now is that we have this guy as well. Okay. And so if you actually write out the dot product and you fill in all the partial derivatives, this will give you exactly our convection term. Okay. All right. Where this v with an arrow over, this is our convection velocity. All right. And so just like we did for diffusion, our goal for this week is to take this equation right here and integrate it over a cell. if we do that, and then we can apply all of our integration tricks that we've done before, things like divergence theorem, things like trapezoidal rule to get an algebraic equation out of it. Okay. And what you'll see from this is that if you kind of remember from fluid mechanics how control volume analysis used to work right there, this is very, very similar to that, or at least the intuition for it is, right? Because basically what we're going to have is we're going to have a cell, like this. So let's say in 2D we have our square cell, and then what's going to happen is that the velocity field is going to be passing through this cell, right? And with that velocity field, it's going to take some of the material with it, right? And so in particular, what we'll look at, and we'll kind of extend our understanding of the flux integral, right? And we'll see basically how the convection velocity transport things across each of the different boundaries of our cell, okay? Right? And so, if you kind of keep that in mind that, we're interested in seeing what the convection velocity passes over the cell boundaries. That's a good kind of intuition to have as we go throughout these equations, because once we start going into the math, as you guys probably are well aware that it's very easy to kind of get lost in the mathematical details. And so when that happens, it's always good to remember physically what's going on, so that you can kind of ground yourself in that instead of trying to figure out all these different integrals and algebras and all those different things. Okay. And just like we saw in the finite difference case, the unique thing about convection is that there's a direction that's imposed on our system, right? And so the velocity field always goes in a certain direction. And when we go to discretize our equations, we have to respect that direction, right? And so if you remember from finite differences, the way we did this was, we replaced our central difference scheme with like a backward difference, sometimes a forward difference, right? In order to kind of make sure that we get a stable solution, right? Either that, we just had to refine our mesh quite a bit, right? And so in order to make our Peckley number less than 2. And so those ideas are still going to be here in finite volumes. It's just that they take a slightly different form because the mathematics are a little bit different. But I want you guys to keep that in mind as we go through the derivations here. All right. So any questions on this so far? Okay. All right. So let's start with kind of the simplest case that we can do, and let's do 1D convection diffusion with finite volumes. All right, and so I'm going to take the the equation that I had on the previous page and write it in its 1D form. Right? And so in 1D, we have d dx of u phi minus k times d dx of d phi dx is equal to q of x. Okay. Right. And so this is our convection diffusion equation in 1D, before we've done everything. Okay. And what we're going to do is we're going to take this equation and we're going to integrate it over a cell. Okay. Okay. And so just to kind of remind you, for a 1D domain, looks like this, right? Okay. When I'm saying that we want to integrate it over the cell, we want to integrate over a space like this. Okay. Okay. And so we'll call the left node right here. So we'll call this XL, okay, for X left. And then on the right, we'll call that XR. Okay. And so we're going to integrate this equation from XL to XR, right? right? And so if we apply our integral, then we end up with the following expression, right? And so we have integral from xl to xr of the convection term. Then we have integral from xl to xr of the diffusion term, and then integral from xl to xr of the source term. Okay. All right. And so from here, we can, we're in the 1D case, so this is pretty simple, okay? Because all of these dx's are going to cancel out here. Okay. Right. And then what we get in the end is a simple kind of integration of each of those terms. Right. And so for the convection term, we have the following, right? So we have u times phi evaluated at xr minus u times phi evaluated at xl, okay, minus k d phi dx evaluated at xr minus d phi dx evaluated at xl is equal to, okay? And on the right-hand side, we're just going to apply our trapezoidal rule. And so we're going to evaluate this at the cell center, okay? And so this is going to be q of xc times delta x, okay? Where delta x, remember, that's the length of our cell. Okay. All right. And so the 1D case, we don't have to do too much with it. A lot of the terms just plain integrate out. Okay. And now what we have to do is we have to evaluate all of these terms. So let me circle them, one of them in red, the other one in blue. Okay. Okay. And so we have to evaluate these terms on the cell boundaries. Okay. Right. And so it's the same issue that we had for diffusion with with finite volumes. And so we're stuck with these terms here in terms of values on the cell boundaries, but we don't want to solve our equations in terms of the cell boundary values, because that would just be finite differences, right? And so what we want to do instead is we want to evaluate these in terms of the cell center values, right? And so what we're going to do next is we're going to take each of these circle terms here and approximate them in terms of the cell center values. All right. So any questions on this so far? Okay. All right. And so what we want to do, is we want to approximate boundary terms in terms of cell-centered values. All right, so let me go ahead and draw a typical cell along with its left neighbor and its right neighbor. All right, and so we have our typical cell here, phi sub c, and of course we have our left neighbor phi sub l and our right neighbor phi sub r. Okay. All right, and then we want to approximate things at xr and x little r and x little l. Okay, and so let's go just kind of one by one, because we have 4 terms we have to approximate. Okay. All right, so let's start with the diffusion terms, because we've done those before. And so the first diffusion term is d phi dx at xr. Okay. And so that's basically the slope of the phi curve at the right boundary. Okay. And just like we've done before, we're going to approximate this with a finite difference. Okay. Okay. And we're going to have the same thing on the left side. Okay. And so this is slope at boundaries. Right. And so what we can do now is we can just take these expressions and just plug it back into the previous equation. Okay. So that's fine. And so now let's do the convection terms now. Okay. All right, and so on the right side we have u times phi at xr. Okay. And so we have a situation here that's unique from the diffusion. So instead of finding the slope of phi, what we want to do is we just want to approximate phi itself. Okay. Right, and so basically what we want is, let me do this in green, is we want the value of phi here. I guess this is on the left side. Let me do it on the right side. Okay. Because x sub little r sits right in between phi sub c and phi sub r, and then from our integration, we need to evaluate this at that location. Okay. So then let me do this. So since we know that x sub little r here sits right in between phi sub c and phi sub r, why don't we just split the difference and say that phi at x sub r is just going to be the average between the two. Okay. All right. And so first we have is u, and we have to evaluate u at x sub r, right? And then for phi, we're just going to take the average. We have phi sub c plus phi sub big R divided by 2. Okay. All right. So that's one of them. Okay. All right. We can do the same thing on the other side. And so the other side is just going to be an average of phi sub c and phi sub big O. Okay. So let me do this in purple. Okay. And so this is going to be u at xl times phi sub c plus phi sub l divided by 2. Okay. Okay. So we're just taking a straight up average between the two, which makes sense, right? Because if we assume that we have basically smooth variation between cell centers, then the value of phi at that boundary is just going to be just the average between the two. Okay. All right. And so now that we have all of these algebraic expressions for the boundary terms, we can go ahead and plug this back in to our governing equation. All right. So any questions on this? Okay. All right, and so once we go ahead and plug this in, we are left with the following expression. All right, and so first we have our, let me write down our convection terms. And so our convection terms, first we have the right term. Okay. Okay, then we have the left term. Okay. And let's just assume for a second that both the u's are the same. Okay. If they're constant. And so there's going to be no dependence on x on that. Okay. This is definitely not going to be on the exam. Yeah. So the last thing on the exam is going to be diffusion with finite volumes. And so for the first midterm, we're running a little bit behind schedule, and so I had to go over just for a tad. But this one's definitely not going to be on the exam. Yeah. Yeah, we're right on schedule right now, so we don't have to worry about that. Okay, and so now we have our diffusion terms. Okay, so we have phi sub r minus phi sub c divided by delta x. Okay, then we have phi sub c minus phi sub l divided by delta x. Okay, and this is all equal to q at xc times delta x. Okay. All right, so this is good. So now that we've plugged in for all of those expressions there, all that we're left with here is an algebraic equation. Okay. And so let's take this equation and let's simplify it by grouping like terms. Okay. And so if we group the like terms, what we get is, first let's do the coefficient for phi sub L. Okay. That's going to be minus u divided by 2 minus k divided by delta x.
Quick question.
Yep.
When you put q of x, comma, is that supposed to be blank?
No, it's phi sub c. So it's q evaluated at the centroid of the cell.
Okay.
Yeah. Okay. Then we have our phi sub c term. So that's 2k divided by delta x. Okay. Then we have the phi sub r term. So that's u divided by 2 minus k divided by delta x. Okay. Phi sub r. Okay. And all this is equal to the source terms. Okay. And so you'll notice here that I don't really do any, I don't really multiply by delta x or anything like that, just because I just kind of find it more convenient to keep it in this form. Okay. Right. And so this is it. And so this is basically our finite volume equation for 1D convection diffusion. Okay. Right, and so just like we've done in the past, in order to use this equation here, you have to have both a left neighbor and a right neighbor. And so this is strictly for just the interior nodes. Okay. Right. And so what we'll go over next is how we can modify this equation for the boundary nodes, okay, which are have the boundary conditions applied to them. Okay, so any questions on this so far? Okay. All right, and so now let's take this equation and let's modify it for our boundary conditions. All right. And so just like we saw for diffusion FEM, which is different than finite differences, is that boundary conditions are going to modify our equations instead of creating a whole new one. Okay. And I find that, especially when you're doing these kind of the first time and you're still kind of building up your intuition, go straight from, from the equation form of this and then plug in your boundary conditions from there. Okay. I'll show you what I mean by that in a second. So let's first do Dirichlet boundary conditions. Okay. And remember, the thing about Dirichlet boundary conditions is that they're a straight up prescribed value. Okay. A straight up prescribed value of phi on the boundary. Okay. So let's go ahead and draw a boundary cell. Okay. And let's say that on the left side of the cell, we have a prescribed value of phi naught. And so in this example here, we basically have a Dirichlet boundary condition on the left boundary. Okay. Okay. And so let's go ahead and write down our finite volume equation, kind of before we plugged in the boundary terms, and let's see how the boundary condition modifies this. Okay. Oh, is the screen flickering for you guys? It's hard for me to notice because I'm already I'm kind of looking down on the iPad. Okay. Well, you can the recording will also be up later too, so you can check it out there. Okay. And so let's go from this form of the equations here. Okay. And so this is kind of before we plugged in our approximations for the boundary terms. Okay. And so this is the form of the equation, before we plugged in our boundary terms. Okay. And so now what we're going to do is we're going to modify these terms to account for the Dirichlet boundary. Okay. In particular, because our Dirichlet boundary condition is on the left, we're going to modify all of these guys that have to do with that. Okay. Okay. And so let's go one by one here. And so, we have basically two terms that we need to deal with. Right. But for all the other terms, we can go ahead and leave them alone, right? And so first thing we have is a phi at x sub r, right? And so we're going to make this equal just to the average between phi sub c and phi sub r. Okay. And so we don't do anything to that term because we have our right neighbor here, and so that's that's fine. Okay. And then for the other one, since basically what we're looking for is the value of phi on that left boundary, we already know what that is because it's our prescribed Dirichlet boundary condition, right? And so let's just go ahead and fill that in. Okay. And so the convection term basically turns into one term that stays the same, and then the other one is just straight up kind of replaced by the Dirichlet boundary condition. Okay, so now let's do the diffusion term. So for the diffusion term, just like the previous term, the one on the right boundary is still going to stay the same, right? And so this is going to be phi sub r minus phi sub c divided by delta x. Okay, and so that doesn't really change at all. But the next term does, because that's the slope of the line on the left boundary. And so we're going to make the same modification that we did before. And so we're still going to use a finite difference approximation. Okay. But instead of going all the way to the left neighbor, we're going to incorporate the Dirichlet term. Okay. And then instead of dividing by delta x, we're going to divide by delta x divided by 2, because it's only half the distance. Okay. All right. And so now that our equation like this, all we have to do is just simplify, right? Simplify, and then also note that since phi naught is a known quantity, we can go ahead and just move that over to the right-hand side. Okay. All right. So any questions on this? Okay. All right. Is the k term on the second to last line xl or xc? This is x. This first one here is xr, and this one here is xl. Yeah. Mm-hmm. Right. Mm-hmm. Okay. All right. And so let's go ahead and do that. And so everything with phi naught, we're going to move over to the right-hand side. Okay. And then if we simplify the rest, then this is what we get. So we have u divided by 2 plus 3k divided by delta x, phi sub c, okay, plus u divided by 2 minus k divided by delta x, phi sub r is equal to q at xc delta x, okay, plus u phi naught plus 2k phi naught divided by delta x. Okay. Right. And so this is the algebraic equation for for the Dirichlet condition on the left-hand side. Okay. All right, so I've boxed this equation here, but just like we saw from diffusion with finite volumes, the equation itself is not really the important part, right? So when you're doing these finite volume problems, what's really important to know is basically how we went about this process of deriving this equation, right? Because every boundary condition is going to be a little bit different, and then this is depending on which side it's on and the sign of the velocity and the sign of the diffusion term, okay, whether in 1D or 2D. And so every case is a little bit different, and so it's a little bit hard to come up with kind of general rules for these guys. Okay, and that's especially true, once we get to 2D as well. And so what I want you guys to kind of take away from this is, how do we go about this process of deriving this algebraic equation, and then apply this kind of same process into future problems. Okay. Okay. And so that's the how we deal with Dirichlet boundary conditions. Okay. And so now let's see how we look at Neumann boundary conditions. All right. And so the Neumann boundary conditions, remember, we look at the Neumann boundary conditions a little bit differently in finite volumes than we do in finite differences. Because in finite differences, when we said Neumann, what we meant was kind of the slope of the solution at the cell boundaries. Okay. But for finite volumes, a Neumann boundary condition means a prescribed flux at the boundary. Okay. And flux, remember, the way that we define flux is kind of that's that's kind of like the transport of that material across that boundary. And then now that we have convection here, we have both convection flux as well as diffusion flux. Okay. All right. So let's do an example of how we would derive the equation if the Neumann boundary condition was on the right. All right. So let me go ahead and draw the domain. Okay. Right. And then on the right side of this domain right here, we're going to have a flux, and this is going to be equal to gamma. Okay. All right. And so let's do the same thing as we did before. So let's write out the equations. But this time I'm going to organize the terms a little bit differently. Okay. Because I'm going to organize them in terms of a flux on the left-hand side and a flux on the right-hand side of the cell. Okay. But let's start with just the equations. Okay. All right, so first we have the diffusion term. So the diffusion term is going to be U times phi at xr minus phi at xl, okay, minus k d phi dx at xr minus d phi dx at xl, okay? And this is all equal to q at xc delta x, right? And so this is our starting point. And so what I'm going to do here is I'm going to organize this term, or organize the left-hand side of this equation so that we have all the xr terms grouped together and then all of the xl terms grouped together. Okay. And so if we first we do xr, and so for the xr terms we have u phi at xr minus d phi dx at xr. Okay. Then we subtract everything for xl. Right? Okay, so we have first u times phi at xl minus, I forgot the k times d phi dx at xl. Okay. And this is equal to q at xc times delta x. Okay. All right. And so I organized this term, the equation in this way, because now we can say that the first bracketed term here is going to be the flux on the right-hand side of the cell, and the second bracketed term is going to be the flux on the left-hand side. Can I rewrite k? Looks like an asterisk. Okay. Yeah. Let me rewrite this whole thing right here. Yep. And then we do this one. Just like that. Okay. Okay. All right. And so for this particular cell right here, we have a prescribed flux on the right-hand side, right? And so what we're going to do is we're going to take this entire bracketed term right here, and then we're just going to replace this with gamma, which is, you know, the flux on the right-hand side. Okay. Right. And so that's going to knock out a bunch of our terms here, which is nice. And then for all the other terms, we're just going to keep it the same. So we're going to use basically the same approximations as we did for kind of the base case. All right. So any questions on this? Okay. All right. So let's go ahead and do that. All right. And so if we replace that entire first bracket term with gamma, all we just have is just gamma right there. Okay. And then for the other terms, we have our usual approximations. Okay, so we have gamma minus u times phi sub c plus phi sub l divided by 2, okay, minus k phi sub c minus phi sub l divided by delta x. Okay. This is equal to q of xc delta x. Okay. And then let's go ahead and rearrange this. And in particular, let's move the gamma term to the right-hand side because it's a known quantity, right? And then what we get from this is minus u divided by 2 minus k divided by delta x phi sub l plus minus u divided by 2 plus k divided by delta x phi sub c is equal to q at xc delta x minus gamma. Okay. And so that's kind of the process that you have to go through to account for a Neumann boundary condition on the right. Okay. All right, and so remember, this equation itself is not that important, but the process that we went through in order to get this equation, that's what I want you guys to remember. Okay. All right, and so we're going to run through this basically one more time, for a Dirichlet boundary condition and a Neumann boundary condition, but we're going to do it within the context of an example. Okay. All right, so any questions on this before we dive into that example? Okay. And so for this example, let's consider the following equation, right? And so let's say that we have 5 du dx minus 8 d squared phi dx squared, okay? And this is equal to 3x, right? And we're going to work on the domain 0, which is less than or equal to x, which is less than or equal to 1. Right? And so our domain just goes from 0 to 1. Okay? And let's consider a case where we have 4 cells. Okay. And so our grid looks something like this. Oops. Okay. And so we have cell 1, cell 2, cell 3, and cell 4. Okay. And so that's good. And then let's consider the following boundary conditions. And so I'm going to deviate from the lecture notes a little bit just so that I give you guys a separate look. But I'm going to basically swap the boundary conditions. And so let's have a Neumann boundary condition on the left and then a Dirichlet boundary condition on the right. Okay. And so let's say that the flux at x is equal to 0 is equal to 3. Okay. And then the Dirichlet value at x is equal to 1. This is going to be 10. Okay. All right. And so now that we have this, we can go ahead and start writing out the equations. Okay. All right. So any questions on this so far? All right. All right. And so first thing we can do is we can write out the equations for the interior cells. Okay. Because those are going to follow the same pattern no matter what. All right, and so our interior cells here are 2 and 3, okay? And so let's go ahead and write out the equations for those guys. Okay. And just because it'll help us about a bit later, let's go ahead and write down the values of all the parameters. Okay. And so the value of u is going to be 5. Our value of k is 8. And our q at xc or q of x, I should say, is equal to 3x. Okay. All right, and so let's go ahead and plug this into our equation. Okay. And so for the interior nodes, remember our equation is the following. And so we have minus u divided by 2, okay, minus k divided by delta x times phi sub l, okay, plus 2k divided by delta x phi sub c plus u divided by 2 minus k divided by delta x phi sub r is equal to x at xc delta x. Okay. All right. And so delta x in this case, because we have 4 cells and the length of our domain is 1, delta x is just going to be 1/4. Okay. And so if we plug all this in and do all the arithmetic, we end up with the following 2 equations. All right. So first for cell 2, what we have is minus 34.5 times phi 1 plus 64 phi 2, okay, minus 29.5 phi 3 is equal to 3/4 times x2. Okay. Right. And then we can write out the next equation for cell 3. And so for cell 3, we have minus 34.5 phi 2 plus 64 phi 3 minus 29.5 phi 4 is equal to 3/4 x3. Okay. And so that's 2 equations down, without too much work. Okay. All right. Any questions on this so far? Okay. All right. And so that's the interior nodes. And so now let's start working on the boundary nodes. Okay. So let's start with the right boundary because that's where the Dirichlet boundary condition is. Okay. And in particular, the right side, the rightmost cell here is cell number 4. And so that's, that's the cell that we're going to work on. Okay. All right. And so just like we did in the previous, 2 examples, let's work off the let's work off the equation, before we plugged in our approximations. Okay. And so let's start here. Okay. So we're going to have u phi at xr minus phi at xl, minus k times d phi dx at phi r minus d phi dx at xl. Okay. And this is equal to q at xc times delta x. Okay. All right. And so since the Dirichlet boundary condition is on the right side, we're going to modify all of these terms with x sub r in them. Okay. All right. And meanwhile, we're going to leave all of the terms with x sub l. Those are going to be unchanged. So you don't have to worry about those ones. Okay. All right. And so let's go ahead and modify those terms. All right, so first we have phi at x sub r, and so phi at the right boundary here, that's the same as our Dirichlet boundary condition. Okay, so let's go ahead and plug in phi naught here, where phi naught here is 10, I believe, right? Yes, phi at 1 is equal to 10. Okay. Right. Okay. Then we have phi at xl, and so that's going to still be the same. Okay, and so it's going to be phi 3 plus phi 4 divided by 2. Okay. Right. Next, we have the slope of phi at the right boundary, and so we're going to modify this in order to account for the Dirichlet boundary, and so this can be phi sub phi naught minus phi 4 divided by delta x divided by 2. Okay. And then the next term we're going to leave unchanged. And so that's going to be phi 4 minus phi 3 divided by delta x. Okay. And this is equal to q at x sub c times delta x. And so this is 3/4 x 4. Okay. All right. And so now all we have to do is we just have to simplify this guy. Okay. And so I don't have the numbers for this, and so I'm going to go ahead and plug it in real time, and probably make several mistakes here, but that's okay. That's part of doing the mathematical process. And so before I do that, are there any questions on this? Okay. All right. And so let's go ahead and start plugging in. Right. So I'm going to start with the first term, and so the first term, since u is equal to 5, we have 5 times 10, and so we have 50. Okay. All right. Next, we have minus, let's see, 5 divided by 2, so that's 5 over 2. Okay. Phi 3 plus phi 4, okay. And so we can leave those alone. Okay. Next, we have minus k, and k is 8 right here. Okay. Right. Then we have delta x divided by 2. And so since delta x is 1/4, so then we have divided by 1/8 here. Okay. 1/8 times phi sub 0, which is 10, minus phi 4, right? Minus, let's see, divided by 1/4. And then we have phi sub 4 minus phi sub 3. Okay. And all this is equal to q of xc times delta x. And so we have 3/4 x4. Okay. Let me just double check. Yeah. Okay. And so now that we have this, we can go ahead and start moving things over, right? Because this 50 and this 10 right here, these are all constants that we know already. And so we can move those to the right-hand side. All right. And so on the left-hand side here, we have a minus 5 over 2 phi 3 minus 5 over 2 phi 4, right? Let's see, so we have minus minus plus, plus 8 times 8, which is 64, phi 4, okay? Minus 32, or say plus 32 phi 4, minus 32 phi 3, okay, is equal to 3/4 x4 minus 50 plus 640. Okay. And so the minus 50 comes from, the 50 right there, and then the 640 comes from the 8 times 8 times 10, and so that's 640. Okay. All right, and so now let's go ahead and combine all the terms on the left-hand side. Okay. And so first we have all the phi 3 terms. Okay. And so for all the phi 3 terms, we have minus 32 minus 5 over 2. Okay. And so that's going to be minus 32 minus 5 over 2. That's minus 34.5. Phi 3. Okay. And then for the phi 4 terms, we have 64 plus 32 minus 5 over 2. And so that's 93.5. Phi 4. Okay. And this is equal to 3/4 x4 plus 590. Okay. And so this is our equation for cell number 4 right here. Right. All right. And so that's kind of in real time, basically, how you would do all these calculations. And so, a little bit more detailed than what we did before, just because, I had to do all the work here. But hopefully that makes things make a little bit more sense. Okay. And so that's the Dirichlet condition on the right side. And now let's do the Neumann condition on the left. And so just like we did on the previous example, we're going to replace the entire flux term with that condition, right? And so let me go ahead and write out our equation here in flux form. And so I'm going to separate kind of the flux on the left side of the cell and the flux on the right-hand side, okay? And so that's the flux on the right-hand side. And so our flux consists of both the convection term as well as the diffusion term. Okay. And then we have the same things on the left-hand side. So we have U phi at XL minus K d phi dx at XL. Okay. And this is equal to Q at XC delta X. And so now what we're going to do is we're going to take this entire flux term on the left side, because remember our Neumann condition's on the left, and then replace that with the flux value. Okay. And meanwhile, on the right-hand side here, we're going to keep these guys exactly the same. All right, any questions on this before I go ahead and do it? Okay. All right, and so if we go ahead and do that, what we have is U at phi sub r, at phi sub xr, right? And so for cell number 1 right here, that's going to be the average between phi 1 and phi 2. Yep. Mm-hmm. Yep. All right, and so phi at xr right here is going to be phi 1 plus phi 2 divided by 2. Okay. Minus k times phi 2 minus phi 1 divided by delta x. Okay. And then from this, we're going to subtract the flux term on the left, right? And so the flux term on the left, let me just go back to my notes. We said the flux was equal to 3. Okay. Okay. All right. And so this is all equal to Q at XC, which is 3/4 times X1. Okay. All right. And so if we move this 3 over to the right-hand side, because it's a known quantity, right? Then we can just plug in for the other terms. Okay. All right. And so what this should give us is, this should give us a, let's see, a minus 29.5 times phi 2, okay, plus, let's see. And so we have 8 times 4, okay, plus 5 times divided by 2. So we have plus 34.5 phi 1, okay? And this is equal to 3/4 x1 plus 3. Right? And this is the equation for cell 1. Okay. All right. Okay. And so remember, Neumann conditions are a little bit easier in finite volumes just because we can kind of replace that entire term. Okay. All right. Any questions on this before we look at the MATLAB implementation? Okay, so let me go ahead and switch to my laptop here. Okay. All right, and so this is a code that I've posted onto Canvas already, and so you know, you can view this code there, or you can just follow along here if you want. Okay. All right. And so the title of this code is basically, 1D finite volume convection diffusion, right? And so this is basically just a 1D problem with convection diffusion, which we're going to solve with finite volumes. Okay. All right. And so the first thing we see is that we have this first part of the code here, which is the same as we always do. And so we define the number of cells, we define the grid spacing. For finite volumes, we have to have this line of code here, which finds the locations for all the cell centers. Okay. Then we had to define the left-hand side matrix and the right-hand side vector, and we define our quantities here. Okay. One other thing that you'll see here is that I'm computing the Peclet number, right? And so this should hopefully look familiar to you guys. Right. Okay, so this is our Peclet number. I don't know why it's doing that. I just want tab, okay? And because remember, in order for it to have a stable solution here, the Peclet number has to be less than 2, right? And so far, what we've done is we've basically just done the same thing as the central difference scheme. And so, in order for this to be stable, Peclet should be less than 2, which it will be. You'll see. Okay. All right. And so now we enter the main loop here. And so in the main loop, this is kind of the same thing we've seen for a lot of these codes. The only difference now is that we're applying things for finite volumes instead. All right, so first thing we do is we loop over the cells, and so we loop from 1 to n. Okay, then we check to see if we're on the first cell, right? And so if I cell is equal to 1, then we're on the left-hand side. Okay. I apologize. So this code right now is it's configured to be kind of the original version of this problem where the Dirichlet boundary conditions on the left. Okay. And so if the Dirichlet boundary conditions on the left, then you have these coefficients. And so we have the coefficients for phi sub I or phi sub c right here. Okay. And we have the coefficients for the right neighbor, right? And so it's the right neighbor because we have I cell plus 1 right here. Okay. And so we have all of that. And then we have the terms in the right-hand side vector. Okay. And so here we have the forcing term plus the velocity term times the Dirichlet boundary plus the diffusion term times the Dirichlet boundary. Okay. All right. And so the next thing we check to see is if we're on the right boundary. And so if we're on the right boundary, in this case, we have the Neumann boundary condition. Okay. Then we assign the appropriate coefficients for phi sub c as well as phi sub l. Right. And then we have the right-hand side vector as well. Okay. And you can see here we have the 3 for the Neumann boundary condition. Okay. And then the last case here is we have our interior cell, right? And so for the interior cells, we just apply the coefficients for all the terms. And so there's the coefficient for phi sub c, this is the coefficient for phi sub r, and this is the coefficient for phi sub l. Okay. And we have the right-hand side vector. Okay. Then once all these values are set, we can just go ahead and solve the system and plot. So let's go ahead and run the code and so we can kind of see. Okay. And you can see from this that the Peclet number is very much less than 2. And so, we have no problems being stable here. And we get a solution that looks like this. And so in addition to the finite volume solution, I've also plotted the exact solution for you just to prove to you that this is working, right? But if we change this to, let's change this to 4 cells. And you can see here that there's a little bit of a difference in between the finite volume solution and the exact solution, right? As you can see, the finite volume solution kind of skirts right underneath it, right? But it converges very quickly. And so, if we increase this to, let's say, 10 cells, okay, right, then we're back to matching pretty much exactly, right? And so this shows that finite volumes is a good method. And so through this method, we were able to determine a solution that matches the exact one pretty closely. Okay. All right. So any questions on this so far? Right. So this code's available for you guys, and so you can use it as a reference for your. I mean, not for this homework, but for homework 6, which is going to be after the midterm. Okay. And so remember what I've always said. So I'm providing you guys these codes, and it's a lot of codes that I'm providing you guys. With the hope that you would use them as references for your homeworks and for your projects as well, right? And so definitely go off these codes, as reference. But remember, you can't just copy these codes and expect them to work, right? And so I think the challenge for you guys is to take kind of these example codes here and modify them, in order to match, either the homework assignment that you're doing or the final project. Okay. And so that's the implementation for a 1D convection diffusion, right? And then now let's talk about upwinding a bit. Yeah, if you're using Python, of course, then you have to convert the codes to Python, definitely. All right. Okay. All right, and so that's basically an example for how you do the hand calculations as well as the code for a 1D finite volume. And so now let's talk about upwinding, right? Because remember, upwinding was something that we had to deal with finite differences because we often found ourselves in unstable situations. Okay? Okay. And so let's kind of remind ourselves, what upwinding is and why we need it. Okay. And so let's kind of jog our memories back to when we did convection and finite differences. Okay. Okay. And so in finite differences, we saw that we sometimes obtain unstable solutions when we used a central difference scheme for the convection derivatives. Okay. Because remember, the convection derivative is a first order derivative, right? And so when we applied central difference to that, then depending on our grid spacing and depending on the velocity, we obtained some unstable solutions, right? And the way that we checked that was we checked the Peclet number, right? So remember, PE was U times delta X divided by K, okay? And in order to get a stable solution, this has to be less than 2. And so one way for us to obtain a stable solution for finite differences, if we wanted to use a central difference scheme, was to refine our mesh until delta X was small enough, right? And we want to do that sometimes because we know that central difference was kind of, the best thing that we can do, or the best in terms of accuracy, the most accurate scheme that we can use for that convection derivative, right? Okay. And so we have this exact same problem in finite volumes too. So in finite volumes, we do get unstable solutions, right? And the way that we refine the grid is we just increase the number of cells, right? And so we increase the number of cells, we reduce delta X, and then that lowers our Peclet number, okay? Right, but sometimes, as we talked about, sometimes it's just not feasible to refine your mesh in order to get a stable solution, right? And so sometimes, your computational cost is just so high, and this is probably most likely true for a 3D situation, that it's just not practical to, to decrease the mesh size even more, right? But if you're still getting unstable solutions, like that's a problem. And then, and so we needed a way to deal with this in order to get a stable solution without having to refine the mesh. Okay. And the way we did that was we changed our our discretization scheme from central difference to an upwinding scheme. Right? And I'll show you kind of exactly how to do that with finite volumes as well. All right. So any questions on this? Okay. All right. And so another option to make stable is to use And so I use the term upwinding here just to be kind of general, because upwinding can refer to either a forward difference or a backward difference. Right? Oh, question. So how much larger in magnitude is a 3D versus a 2D? Is it dependent on the size of the new dimension? It's part of that, yeah. But the equations also just get a lot more complicated in 3D as well, just because you have a lot more neighboring terms, and so it's tough to really say because it depends on the problem. But generally, you can expect the cost of a 3D simulation over a 2D simulation to be roughly about, I would say 8x bigger, and so it's a pretty significant increase. Yeah. Okay, so we're out of time, and so I'm going to leave you with this thought right here. Okay. So if you let me go on for just a brief second. Okay. Right. And so, this is our usual finite volume scheme, right? And so we have our central cell, we have our left cell and our right cell, right? Usually what we had to do for the convection terms, where we had to approximate the value of phi at this location, was we did just the average between them. Okay. And so on the left side, we have phi sub L plus phi sub C divided by 2. And the right, we have phi sub C plus phi sub R divided by 2. Okay. All right. And so this, if we use this scheme right here, this is basically the exact same thing as a central difference scheme, right? And so what we'll see on Wednesday is that if we replace these with an upwinding scheme, okay, we'll be able to achieve the same stability results as we did in finite differences, but for this finite volume scheme. Okay. All right. So any final questions on this before we sign off for today? All right, so that's all we got time for. So thank you guys for tuning in today. And so take a look at the study guide that I've posted, and and be ready to vote on the poll when it comes out. Right. And so thank you guys for tuning in. Have a good rest of your evening, and I'll see you guys on Wednesday. All right, thanks, guys. Thanks, guys. Thanks, Marcos.